So this is how we solve Chapter 5, problem number 66. What we have here is a slope, and we have a box sitting on this slope. And this box, we are applying a force to push it. Some force push. The box has a mass of 100 kilograms. And it goes at an acceleration equal to 2.0 meters per second squared. And the angle of this slope is equal to 30 degrees. And we're asked to find what is F push. So to do this, we solve it the same way we solve every kind of problem on an incline. Instead of having our axes kind of left and right with the XY axis, kind of X going left and right and Y going up and down, we rotate this so that the X is now going along the incline and the Y is perpendicular to the incline. So that's going to kind of change the picture that we need to draw. So the first step is going to be to apply this rotated coordinate system into our free body diagram. And to draw the free body diagram, we have to draw all the forces that are acting on this box. We have gravity, and gravity goes straight down. That's my force of gravity. We have the normal force. The normal force goes perpendicular to your surface. So since we're sitting on an incline, our perpendicular is kind of up at this angle. Right? We want to be perpendicular to this slope. And then what I need to do is I need to take this force of gravity, which is now acting at an angle relative to my rotated coordinate system. See here where my X is kind of going slanted. I need to rotate my coordinate system. I need to break this force of gravity into X and Y components that work with this new rotated system. So the easiest way I found to do this is to take that normal force, which is pretty clear to draw the normal force perpendicular to the slope, and then I extend this backwards. And it goes back to give me the Y component of my gravity. And then the X component of that has to be parallel to the slope. So here's my slope, and I can imagine drawing this line, drawing this slope to complete this triangle for gravity, so that this dotted line, this FGX, is parallel to the slope. So this is my free body diagram. And now I can use this to write out all the forces that are acting in this problem. Let's clean this up just a little bit. And let's start working on my forces. So like projectile problems, we need to do things in the X and Y directions. We need to separate directions. So the sum of forces in the X direction, I would first identify what forces are going up the incline. And it looks to me like there's only one force that's pushing up this incline in the positive direction. That's going to be force of push. So I have F push. And then I identify any forces acting down the incline. The normal force is acting kind of up in that Y direction. FGY is acting directly down. FGX, though, is pulling me down the incline. So I'm going to subtract off my FGX. And that's going to be equal to the mass times the acceleration. And now I take stock of what I'm trying to find. I'm trying to find F push, so I can solve this equation for F push. F push is equal to mass times acceleration plus FGX. I do that by adding the FGX to the other side. So this is algebra skills. F push is what I'm looking for. I know what the mass is. They gave me that up here. I know what the acceleration is. They gave us that acceleration. Now I need to find what FGX is. And to do that, I need to recognize that this angle, this 30 degrees, is the same as this angle. So if you draw your pictures this way for things on inclines, this will always work for you. It's a little bit of geometry to figure this out, but it always works. So we have that 30-degree angle, and I can now find what FGX is in terms of Fg, the force of gravity. And we'll see why that's useful in just a moment. Now this angle is 30 degrees, and my FGX is on the opposite side. Because it's the opposite side, and I'm trying to relate the opposite side and the hypotenuse, I can use the sine. So I know that the sine of 30 degrees is going to be equal to this opposite side, FGX, over the hypotenuse, FG. I can solve this for FGX and see that FGX is equal to FG times sine of 30. And Fg is the force of gravity. So that means it's not only G. It's a common mistake students make. They say Fg is G. Fg is the force of gravity, so it has to be equal to the mass times the gravity. So Fgx is equal to Fg, the mass times the gravity, times sine of 30. Again, force of gravity, Fg, is equal to mass times the acceleration due to gravity. You got to remember that. And now I can take this and I can plug it in. F push is now equal to mass times acceleration plus mass times acceleration due to gravity times sine of 30. And taking stock, I know all of these values. I can plug these values in. F push is now equal to 100 kilograms times the acceleration we were given of 2.0 meters per second squared plus 100.0 kilograms times 9.8 meters per second squared, the acceleration due to gravity. And we use a positive 9.8 because we took care of the fact that it's negative right here when writing our sum of force equations. And then I multiply again by that sine of 30. So here I'm just plugging numbers in. The mass, the acceleration, the mass again, the acceleration due to gravity, and the sine of 30. Plug all this into your calculator and you will see that F push is equal to 690 newtons. And that's how you do problem number 66 in chapter 5. 690 newtons.